Okay, so in today's lecture, which there'll be two parts to it, we're going to discuss sequences and their limits. So from the textbook, this is section 3.1, sequences and their limits. Okay, now this is a fundamental concept in real analysis, of which we will build a lot of the more major theorems in the course. So it's a very important beginning section for the rest of the semester. So with that being said, let's start with the fundamental definition of a sequence. 3.1.1 definition. Okay, so what is a sequence? So a sequence say a sequence of real numbers is a function defined on the set of natural numbers whose range are real numbers. So whose range is contained in R. So that's all a sequence is. It's a sequence whose input is a set of natural numbers, and what you get out is a collection of real numbers. Well, a sequence of real numbers is defined this way. So, sequence of real numbers is defined as this. Okay? So maybe in like a Calculus 2 course, you would have come across sequences, or maybe in a pre-cal course even. But the way that we're going to define them in this course in real analysis as a function from the natural numbers to R. And we're going to adopt certain notation. So the notation is actually very important to pause on for a moment. So I'm going to make a note of this for notation. Okay. So if X is a sequence in R, okay, we will denote the image of the natural number n. So again, x of n. That's how you would typically do that with a function, right? But for sequences, we would denote the image of n by little x of n. And x, the sequence itself, the function, by, well, there's three different ways to do this. We can define it just by x, or denote it just by x, I mean. We can say parentheses xn, or we can say parentheses xn such that n is a natural number. So these are the three different ways that we would define the sequence itself. And for the image of a sequence x, of a number n, we'll write xn, or an or bn, whatever it be the case. Okay, now the use of parentheses here is, it's used to indicate that there's an ordering on the sequence. Like technically, a sequence is a collection of, it's a range of a function, right, which is a set. But for sequences, we're going to emphasize that the ordering matters. So these are like infinite tuples, if you will. So that's why we use the open parentheses instead of curly braces to indicate this set of numbers, because the ordering does matter. Now, sequences as functions can be defined in several ways. So sometimes, I'll go ahead and say like, so sequences can often be described in two different ways. So sequences are often defined by a formula or recursively. So a formula is an explicit representation of the function of the sequence. So for example, the formula may be like something like the sequence xn is equal to 1 over 2 times n, such that n is a natural number. So this would be an explicit way of defining the terms of that sequence. Recursively, you can think of something like maybe the Fibonacci sequence, where f1 is equal to 1, f2 is equal to 1, and then fn is equal to fn minus 1 plus fn minus 2. And this is for n greater than or equal to 3. So this would be a recursive definition where the new terms in the sequence are defined in terms of one or more of the previous terms. And hopefully all of you have seen this Fibonacci sequence before. Okay. So now we should discuss what it means to have a limit. What does it mean for a sequence to converge? So the limit of a sequence. Okay, so what is this definition? So a sequence X of real numbers is said to converge to, I'll say a number L in R if for every epsilon greater than 0, there exists a natural number k and k is dependent on epsilon. That's why we adopt this notation here. But it's important to remember that this is a natural number, okay, such that for every index n greater than or equal to k, the distance from the sequence at that index minus L is at most epsilon. So this is what it means for a sequence to converge. Now, so if a sequence does converge, then we say that the sequence has a limit. And we'll use the notation limit as xn equals to L. Or another way of writing this is that xn goes to L as n goes to infinity. Okay, so this is the definition of convergence. Now we should take a moment to maybe talk about this definition. So let's just kind of imagine what is this definition trying to capture, right? So let's just for the moment suppose that the sequence xn converges to L as n goes to infinity. Let's just take a moment and just kind of imagine that some sequence satisfies this definition for some real number L. So, okay, now what is a sequence? A sequence is a function whose domain is the natural numbers and whose codomain is some set of real numbers, right? So we can imagine if we denote our sequence by x, right? And we have all of the natural numbers right here. And then we have the real numbers over here. And then maybe right there, there's some L. Okay? And we're supposing that this sequence that maps naturals to the reals, right? That's what this does, right? We're supposing that sequence converges to that number L. So looking back at the definition, what does that mean? It means that if we pick any epsilon greater than 0, there is some natural number, k, right? So that if the index for the sequence is greater than or equal to k, then the distance from xn to L is less than epsilon. So we're going to be concerned with distances here, right? So let's pick some arbitrary epsilon. And let's look at distances around L. So that's distance. So if we look to the right, that's L plus epsilon. And this is L minus epsilon, okay? And then we have all the natural numbers in here. So it's maybe 1, 2, 3, 4, 5, 6, forever, okay? And each of those natural numbers has an image under the sequence. So for example, let's suppose that the index for epsilon that we get is 6, okay? So there has to exist some index, and I guess it would be 6. So maybe x of 1 is mapped right there. But then maybe x of 2 is mapped right there. And then x of 3 is mapped right here. Maybe x of 4 is mapped right here. And then maybe x of 5 is mapped right there. So this is what our sequence looks like. But then, if that was the correct index for our epsilon, for every natural number greater than or equal to k, the sequence, the image of that natural number, needs to be within epsilon to the limit L. So we guessed it was 6, but we're just supposing it's 6. So that means that that number right there, that's x of 6, right? So then that means that the distance from x of 6 to L needs to be within epsilon. But then every other element past x of 6, maybe like that's x of 7, and maybe there's 8, and maybe here's like x of 8. And everything else, every other natural number needs to be mapped within that distance epsilon to L, okay? So this is what it's saying. It's saying that if a sequence converges to some limit L, then at some point there's a cutoff. In this case, it happened to be 6 for this example, right? There's a cutoff where every image for that sequence after that cutoff, anything bigger than that number k, is going to be within epsilon distance to the limit. That's what this definition is trying to capture, okay? And we'll do some specific examples after we prove a theorem about the uniqueness of limits, which we'll do right now. Okay, this is 3.1.4. This is the uniqueness of limits. Okay, so what this says is that a sequence in R has at most one limit. Sequence cannot converge to two separate numbers. Okay, so let's prove it. So suppose that a sequence has two limits. So suppose the limit of xn equals L prime, and at the same time, the limit of that sequence equals L prime. And we can suppose that there's a sequence that does that. Okay? We're supposing that it's convergent, and not only is it convergent, but it has that as its limit and that as its limit as well. So if that's the case, we're guaranteed the existence of a cutoff point, cutoff index, for each of these limits here, where after that index, that is always within some epsilon distance to that and some other epsilon distance to that. So I can just say by definition, yeah. So maybe not by definition. I need an epsilon to start with. I need to pick an epsilon to start with. So then I can say, next, let epsilon be some arbitrarily positive real number, some arbitrary positive real number. So then I can apply the definition to there and there. So then, by definition, there exist natural numbers So I'll say K prime and K double prime, maybe. So that if n is greater than or equal to K prime, then the distance from xn minus L prime is less than epsilon over 2. We'll get to y in a moment. And if n is greater than or equal to K double prime, then the distance from xn minus L double prime is less than epsilon over 2. Now, this holds for, like, the definition of convergence holds for any positive number epsilon, right? Well, I let epsilon be greater than 0. So epsilon divided by 2 is positive. So there is some index, so that if n is greater than that index, this distance is at most epsilon over 2. That's just some positive real number. Just because it doesn't have epsilon by its own, on its own, doesn't matter. It's just a positive real number. And the same thing holds for this limit L double prime. There is some index, so that if n is greater than or equal to that index, then whenever n is bigger than that index, it's at most epsilon over 2. Okay? So then, or maybe therefore, yeah. Therefore, if k is equal to the maximum of those, if k is the maximum of these indices here, these natural numbers, then if n is greater than this k, then that holds and that holds, right? Because if n is greater than that k, then it's greater than k double, greater than or equal to k double prime and greater than or equal to k prime, because it's bigger than or equal to the bigger of the two of them. So if n is greater than that, then that must hold and that must hold. So if k is equal to that, and n is greater than or equal to that k, then if we look at the distance between, so then we can say L prime minus L double prime, that's equal to, what can we say? L prime minus L double prime plus xn minus xn, right? I just added 0, and that's equal to L prime minus xn plus xn minus L double prime. I just grouped them, right? But then I can use the triangle inequality here and get that that's at most L prime minus xn plus xn minus L double prime, right? But now, that's just the distance from L prime to xn, which we know is at most epsilon over 2. And that is also at most epsilon over 2. So this is strictly less than epsilon over 2 plus epsilon over 2, which is equal to epsilon. So what does that mean, right? Well, the distance between L prime and L double prime is at most epsilon for any choice of positive epsilon, any choice, right? So then we can say, hence, L prime is equal to L double prime, and the limits are the same. Done. Because the distance between these two numbers is bounded above by epsilon for any positive number epsilon, which means that they're equivalent. And we've talked about that in the previous lecture. Okay. Okay. So next, let's recall the definition of epsilon neighborhoods. Okay, so recall for epsilon greater than 0, the epsilon neighborhood of x is the epsilon of x, and this is equal to all the set u such that the distance from u to x is less than epsilon. So like here with this picture over here, this would be the epsilon neighborhood of that L, for that epsilon that we chose. Okay. So now we can phrase convergence of a sequence in terms of the original definition and in terms of epsilon neighborhoods, because as you see, there's something going on with how every bit in this sequence is mapped to this epsilon neighborhood. So there is some relation here. And I find it appealing, actually. It makes it easier for me to think about convergence of sequences. So this is, actually, I'll probably need to write it over here. So I'll run out of room. This is the theorem 3.1.5. Okay. So let xn be a sequence in R. And let L just be some real number. Okay. The following statements are equivalent. So the following are equivalent. Part A, xn converges to L. Okay. Part B, for all epsilon greater than 0, there exists some natural number k, which is dependent on epsilon. Remember that? Such that n greater than or equal to k implies x of n minus L is less than epsilon. That's just the definition. That's just the way of saying the words. Part C. For every epsilon greater than 0, there exists some integer k such that n greater than or equal to k implies L minus epsilon less than xn, which is less than L plus epsilon. That's kind of like the picture that I had here before. It's just contained in that interval around the limit L. And finally, for D, for every epsilon neighborhood around the limit L, there exists some natural number k such that if n is greater than or equal to k, implies x sub n is an element of that epsilon neighborhood of L. Okay, there's a proof of this equivalence in the book. It's kind of tedious, but not difficult, just showing that this implies that implies that, these all imply each other. It's not too difficult to show. But basically what this is saying in a sense is that convergence tells us something about like the end behavior of a sequence. Like if a sequence converges to some number, then all of the sequence is contained somewhere, contained close to the limit. So I even made like a note here for you all. So basically, if the limit of some sequence is equal to L, then all but a finite number of terms from the sequence, which is like the range of that function again, belong to the epsilon neighborhood around L for any given epsilon greater than 0. That's basically what we're observing, right? So, for example, like I got that picture I showed earlier. So this is the real number line, this is L, and we're supposing that the sequence converges to L as n goes to infinity. Then for a given epsilon greater than 0, there is some epsilon neighborhood around. So it's like L plus epsilon, L minus epsilon. Like, yeah, like there's terms like x1, right? It might be over here. And maybe like x2 right there. And you could go like a really long way, like maybe dot, 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 like maybe like x100 is right there. But at some point, call it k, there's xk. And then maybe like right here, here's xk plus 1. And then maybe like right there, that's xk plus 2. Every n greater than k, greater than or equal to k, is going to send inside of here. And there's only a finite number. So if k was like 101, for example, then x1, x2, there could be an x4 in there, x3 in there, but it's like kind of maybe jumping around. But eventually, if that sequence converges, after you hit that index, that k, or capital N, or whatever you use, after you hit that threshold, every bit of the sequence belongs to this epsilon neighborhood around the limit, which means that there's an infinite many terms because, again, the sequence has domain natural numbers. There's infinitely many things that are being mapped with the sequence. Infinitely many terms in the sequence needs to be bunched up close around L. That's like the idea behind convergence here. Okay. So this was an introduction to the definition of a sequence, definition of convergence of a sequence. We proved the uniqueness of limits of sequences, and we discussed how we can think of this in terms of epsilon neighborhoods around the limit, provided it does converge. So I'm going to go ahead and stop this recording here, and in the second half of this lecture, we're going to actually work out how to solve, how to prove limits of sequences for a given explicit sequence.